Linjie Zhao. And well, Linjie was a postdoc last year, I believe, no? Linjie in INRIA in Lille with Marielle and Clément Rignot. And today is going to talk about the target particle in asymmetric exclusion with long jumps. Welcome, Linjie. The stage is yours.
Okay. Thanks for the introduction and the invitation. In this talk, we shall discuss the fluctuations for the target particle in asymmetric exclusion process with long jumps. And the plan of the talk is divided into 3 parts. In the first part, we first introduce some references on the target particle and then state the main result of the talk. In the second one, we will give some ideas of the proof. And actually, we only partially solve the problem. So in the end, we will propose some questions. And I think most of the audiences are experts on the exclusion process. So let's go through this model quickly. We consider the process involving an ZD. So at each side of ZD, there is at most one particle. And jumps to occupied sites are not allowed. So in the first picture, this particle cannot jump to its right, but the particle at site X could jump to site Y, and the jump rate is given by P y minus X. So the system is translation invariant. We usually have some general assumptions on the jump rate P. For example, we usually assume it is irreducible. And in the exclusion process, all the particles are the same. They are indistinguishable. On top of the exclusion process, we introduce, we pick up a particular particle, that is the blue particle in the second picture. And we call this particle the target particle. And except this particle, all the others are the same. We want to understand the behavior of this particular particle or the target particle. So we first fix some notations. We use the T to denote the exclusion process. So the configuration space is 0, 1 to ZD. And we use XT to denote the position of the target particle. We usually assume the initial position of the target particle is 0. So X0 is 0. One could check that the target particle is not a marker process. So it is difficult to work on the target particle directly. And it is more convenient to work on the environment process as seen from the target particle. And we denote this process by XT. So XTZ is eta T of XT plus Z. And one could check that the environment process XT is a Markov process. The evolution of the environment process has 2 parts. The first part corresponds to the movement of the normal particles, that is the black particles here. So in the first picture, the particle at site xt plus x jumps to site xt plus y. If we in the environment process, this corresponds to a particle jumps from x to y, and after the jump, this is a new configuration. And the second part of the environment process corresponds to the movement of the target particle. That is in the second picture, the jump of the blue particle. So after the jump of the blue particle, the new configuration is this. So this set becomes xt, and this set is xt minus y, and this set is xt plus x minus y. So if a blue particle jumps, then there is a translation of the environment process. For rho in 0 and 1, we let new rho be the product measure on the configuration space with constant particle density rho. And we let new rho star be the measure of new rho condition on having a particle at the origin. Then it is well known that new rho and new rho star are invariant for the exclusion process and the environmental process respectively. So if we start the process from neutral star, this is called the stationary fluctuation. And when the jump rate P has finite range, stationary fluctuations for the target particle has been well understood. So here are some references. In the one dimension and in the nearest neighbor symmetric case, in the paper of Arisa and Grid and Sander, we showed that the target particle is subdiffusive. Moreover, it converges to a fractional Brownian motion with parameter 1/4. And in all the other cases, the target particle is diffusive, and so the limit should be a Brownian motion. For example, by Kibnis and Varadan proved the symmetric case, and Varadan proved the mean zero case. And in these two papers, the main method is to give a martingale decomposition for the position of the target particle. And for this method, the book by Komorowski, Landim, and Ola is a good reference for this method. In general, the asymmetric case is more difficult. Kibnis proved the one-dimensional and asymmetric nearest neighbor case. The method is mainly based on the mapping between the exclusion process and the zero range process. And for 3 or higher dimensions, this was proved by Sander and Varda and Yang in 3 or higher dimensions. This is because the random walk in 3 or higher dimensions is transient, so they could use some transience estimates for the for this case. And so it remains to in dimension 1 and 2, and in the asymmetric case. In this case, we only know the target particle is diffusive. This was proved by Sander in 2006. And there remains an open problem here. So in this case, we don't have central limit theorem or invariance principles. So these are the references for the finite range case and the stationary fluctuations. Milton in 2009 considered the symmetric exclusion process with long jumps. He assumed the jump rate P to have this form, that is 1/x to d plus alpha for some alpha between 0 and 2. In the theory of hydrodynamic limits, we know this choice of jump rate P is closely related to the fractional operator. And Milton considered the non-equilibrium fluctuations and equilibrium fluctuations for the target particle. He showed that in the equilibrium case, xt and alpha over n converges to a level process. So in this case, the target particle is super diffusive. So as a natural follow-up, we consider the asymmetric case with long jumps. We have the following two assumptions on the jump rate P. The first assumption is the jump rate P is homogeneous. This means there exists alpha larger than 0 such that Pu of n is n to d plus alpha times Pu. This is a very natural assumption, I think, and this comes from the symmetric jump rate. This is actually comes from this jump rate. And the second condition, I assumed the symmetric part of P satisfies the following. So I assume the symmetric part of P is x2 minus d minus alpha. So this is actually this. I think the second assumption is not so natural because the total asymmetric case does not satisfy the second condition. That is, if we only allow particles jump to the up and the right, then we could see that it does not satisfy the second condition. But I assume the second condition only for convenience, and I think the method should work for this case. And in the second part, we will see why I assume the second condition. And it is not hard to find an example to satisfy the above two conditions. For example, we could take P to be this form, where take P to only have drift in the first direction. Okay, now we need to we first consider stationary fluctuations for the asymmetric case. So we let the process start from neutral star, the invariant measure of the environment process. And we denote M, the expectation of the jump rate. So the first step is to normalize xt. So if alpha is between 0 and 1, then we just did nothing. We just speed up the process by n to alpha, as in the symmetric case. And if alpha equal to 1, we should minus the truncation of the jump rate at the level of n. And if alpha is between 1 and 2, we just let xt and alpha minus its mean value. So it's t and alpha times 1 minus 0 times m. And if alpha equal to 2, we have a log n correction here. So we could see that the normalization of the xt is actually the same as for the random walk with jump rate p, except we have an extra factor 1 minus 0 here. And this comes from the probability that a set is empty. The probability of empty set is 1 minus 0. So here we have 1 minus 0. And as in the symmetric case, the limiting process is also a Lavie process with initial condition 0. So we only need to know the characteristic exponent of the Lavie process, and we denote it by phi here. And phi has the following formula. We don't need to care about this formula. We will see how this comes out in the second part of the talk. And we just note that if alpha is 2, then it is actually a Brownian motion. And then this is the main result of the talk. We could show that in the one dimension, if alpha is between 0 and 3/2, or in 2 or higher dimensions for alpha between 0 and 2, then the normalized tagged particle converges to the Lavie process introduced above. We only consider the case alpha less than 2, and for alpha larger than 2, because the jump rate has a finite second moment. So in general, it should be the same as in the asymmetric finite range case. And in the one dimension, we didn't solve the case for large alpha, that is for alpha larger than 3/2. We will also see why we can't solve this in the second part of the talk. And as I said before, actually Newton also considered the non-equilibrium fluctuation for the tagged particle in the symmetric case. But so far, I don't know how to solve this problem for the asymmetric case. And we will come back to this problem in the last part of the talk. So above are the main results. And then we give some ideas of the proof. As in the symmetric case, the main idea is to investigate the exponential martingales associated with the tagged particle. So we first count the number of jumps of the tagged particle in the direction z, and we denote it by ntz. So ntz. So the position of the tagged particle xt is equal to the sum of z times ntz. So this is straightforward. And for ntz, we know it is a compound Poisson process with intensity of the time integral of pz times 1 minus kzz. We remember that we use CIS to denote the invariant process. So if CIS Z is 0, then the particle could jump to Z, and the jump rate is Pz. So this is how this intensity comes out. Moreover, for different Z and Y, NTZ and NTY are independent because there are no common jumps between the two Poisson processes. So actually, Xt is a sum of independent compound Poisson processes. For Poisson processes, we know the exponential martingale. So naturally, we have the following exponential martingale. So this is exponential martingale, and we have the sum over there here because the Poisson processes are independent. The next step is to normalize the target particle. So, sorry, I forgot to say that in the proof we consider the one-dimensional case with alpha larger than 1, and the other cases are similar. So in this normalization, we just let the target particle minus its expectation. So its expectation is T times n to alpha times m and times 1 minus 0. And when we do this, we will have two extra terms. They are marked blue in the second and the third lines. So, so if we want to know the characteristic function of the wave process, then we just need to find the limit of the second and the third lines. And the second line is easier. It could be dealt with as in the symmetric case. So we could show that the second line converges to this term, to this integral in probability. This is not hard to see if we look at the expectation of the second line. So because the process is inflationary, so we could replace 1 minus C Sz by 1 minus 0 here, and the time integral gives T times n to alpha, and we write this sum down here, and then we use because Pz, we assume Pz is homogeneous, so we write Pz as Pz over n of times 1 over n to 1 plus alpha, and cancels this n to alpha, leaves 1 over n here. And if we look at this term, this is Riemann sum, so it converges to this integral. And this is how this integral comes out. And this is actually the characteristic exponent of the limiting wave process. So it remains to consider the third line. And the third line is the extra term when comparing with the symmetric case. And for the third line, we want to, because it is centered, so we want to show it converges to 0. So we first use Cauchy-Schwarz inequality, and we only need to show this term converges to 0. If we look at this term, we see it is additive functional, and because the process is inflationary, so the usual way to bound additive functional of the stationary process is by using the Leibniz-Walden inequality. So we bound this term by C times T and times this inequality here, and this is called H minus 1 norm in the literature. So here L is the generator of the invariant process. This is the generator of the process CS with jump rate P. And for the H minus 1 norm we have the following variational formula. So here S is the symmetric part of the generator I/O, and A is the anti-symmetric part of the generator I/O. The main point here is that the third term is non-negative, so we wanted to find an upper bound, so we could remove this term. And if we remove this term, then we get the H minus 1 norm for the generator S. So we have this inequality. Compare with this term, we just replace this IO by S. So here we replace it by S. And S is the generator of the environment process with jump rate S. And we said, as we said before, it has two paths. One corresponds to the movement of normal particles, and the other to the movement of the tagged particle. We use SE and ST to denote the generators of these two paths, respectively. And the next step is to compare with the H-1 norm of the environment process with the H-1 norm of the symmetric exclusion process. So to do this, we adapt the proof of standard paper in 2006. In this paper, it is in the finite range setting, and we adapt the proof to the long jump setting. The main idea is by using the variational formula for the H-1 norm, we first replace this S by the generator of the normal particles. So by SE here. So this is we just replace S by SE, and we know that SE is corresponds to the movement of normal particles, and actually SE could be seen as an as a symmetric exclusion process on ZD minus 0. And the main point here is that for SE, the process is not translation invariant because the underlying space is not translation invariant. So it is still not easy to deal with this H-1 norm directly. The idea is to compare with the H-1 norm of SE with the H-1 norm of the symmetric exclusion process on ZD. And we could bound this by this term, and here S is the generator of the symmetric exclusion process on ZD. So now it is a translation invariant process, and it is easy to handle with this term. So so far we have shown that the variance of the occupation time could be bounded by this term, by the H-1 norm of the symmetric exclusion process, and it is also a classical result that the H-1 norm of the symmetric exclusion process is associated with the Laplacian transform of the variance of the occupation time. So we could write this term as this term. So we see this is the variance of the occupation time in the symmetric exclusion process with jump rate S, and then this is a Laplacian transform. So this is what we have proved now. And if we change S to ST in this formula, then roughly we have the following formula, following inequality. So this inequality says that we could bound the variance of the occupation time in the environmental process by that in the symmetric exclusion process. Now we change T to Tn alpha. We come back to the original problem, and we have this inequality. So now we need to consider the occupation time of the exclusion process with long jumps, and this was considered by Cedric, Patricia, and Sander in 2016. They consider the jump rate for 1 over Z to D plus alpha. So this is why I assume the second condition. Why I assume the symmetric part of S is given by this formula, just for convenience. And they proved the order of this is n to 2 alpha minus 3, and this is why I could only prove the result for alpha smaller than 3/2. So this is a problem. Okay, above are the main idea of the proof. And this is the final remark about the proof. If we consider the random walk with jump rate s, that is x2 minus d minus alpha, we know that the random walk is recurrent if and only if d is equal to 1 or 2 and alpha is larger than d. And in the trident case, that is if d is larger than 3 or d is smaller than 2 and alpha smaller than d, then we could also use the trident estimates in this paper to prove the result, but only in the trident case. And now, in the last part, I have some questions for the. So the first is the stationary case. In the stationary case, we didn't prove the one dimension for alpha between 3/2 and 2. And in the second part, we see the main problem is to understand this quantity, that is the occupation time of the environment process. So far, I don't know how to deal with this term. And second question is about non-stationary fluctuations for the Higgs particle. So we still start from the exponential martingale, and we normalize the Higgs particle. So we let the Higgs particle minus its expectation, and then we still have two extra terms as in the second and in the third line. In the second line is the same as in the symmetric in the stationary case, and in the third case, here we have the expectation of KCSZ instead of rho, because it is no longer stationary. And for the second line, we couldn't deal with the second line as in the stationary case because we cannot replace 1 minus KCSZ by 1 minus rho as in the stationary case. The main point here is to write the second line as the empirical measure of the environment process by using the homogeneous of the jump rate p. So if we write pz as pz over n of 1 plus n to alpha plus 1, then we have the following formula. And for this formula, we see that the term inside the brace is just the empirical measure of the environmental process. So we could use hydrodynamic limits theory, at least intuitively, to show that this term converges to the time integral from 0 to t comes from here, and then the integral over r, and here e to I beta u minus 1 minus I beta u, and the p of z over n is pu. And for the term 1 minus KCSZ, if we denote rho SU by the hydrodynamic equation of the asymmetric exclusion process, and we remember that KCSZ is eta s, z plus xs. So roughly speaking, KCSZ should be replaced by rho s u plus y alpha s. And remember, y alpha s is the limit of the Higgs particle. So I think this is a technique in Newton's paper. And compared with the symmetric case, we also have the third line. So, and I think this term is a difficult term. And for this term, we need to understand the non-stationary fluctuation for the occupation time of the environmental process. And so far, I don't know how to deal with this term, and that's the reason why I didn't do the non-stationary fluctuations. And for non-stationary fluctuations of the occupation time, the paper I know is by Fons and Xu in 2021, and maybe this paper will be helpful. That's talk of today, and thanks for listening.
Thank you, Linjie.
Thanks.
Very nice your word. Very. You just took 30 minutes. So we have plenty of time for discussions. So I want to ask, is there any questions from the audience at IMPA or in Zoom? You have, yes, Hubert. Go ahead.
Yeah, so okay. Yeah, I don't know a lot about the subject, but in dimension one, I guess the nearest neighbor case is really different because particles cannot overtake one another, right?
Yes.
And in that nearest neighbor case, it turns out that the position of the tagged particle, it's related to the flux of particle at the origin. So in these like alpha stable cases, have you looked at like well, either well, this question of the flux, or maybe another way to state it would be like instead of tagging a particle, you just label all particles so that like the order of the labels is the same as the order of the particles on the line, and yeah, when a particle jumps, you are allowed to change the label, but only of finitely many particles. I think if you do this with these two rules, probably you have a unique definition for your process. And instead of following the tagged particle, you follow the particle with label 0. Do you think you could obtain result for this kind of process, or for or either this process or the flux with this kind of martingale techniques, or do you require something else?
Yeah, the only reference I know for the flux is mostly work on the nearest neighbor case, and yeah, maybe I could try to look at the flux in the non-nearest neighbor case, but I didn't work on this.
Okay, well, thank you.
Yeah, that's a good advice. Thanks.
Yeah.
So
Question?
I have, yeah,
Yes.
so I have a question. So I was trying to remember what I did in this paper a long time ago, and so I think so. So what is how the situation of hydrodynamic limits is for this jump rate, so that is asymmetric jump rates that you are proposing? Because I think it's in dimension one you need some assumptions, because you don't so the 3/2 probably comes from the fact that for alpha between 3/2 and 2 the Burgers terms dominates over the other term, right? And but in dimension I don't know if in higher dimensions what is the situation of this. I mean, I would say that that's a previous question, no? So how is the understanding of the hydrodynamic limit of this model in regardless alpha and dimension?
Yeah, I remember Sander had a paper for the hydrodynamic limits of asymmetric exclusion process with long jumps. But I remember Sander did some work on this.
Yeah, it's there's still an open question there. So for instance, if you take this totally asymmetric jump rate, which is in the top of the screen, Then, so with Daron Shahar, we showed that the empirical measure, in the sense of subsequences, we showed tightness of the empirical measures, but so the limit points satisfy some sort of fractional version of the Burger's equation, but we weren't able to show uniqueness of weak solution to this fractional Burger's equation. So, so that's a could be a, you know, that's an open question. It's at the PDE level, but in the finite range case, we know that we need extra conditions to get the entropy solution, right? So so there could be some extra work to narrow the class that one is looking at in order to prove uniqueness, and so what that narrowed class would be, we didn't pursue. And the alpha in the occupation time in one dimension. So in that paper with Cedric and Patricia, we conjectured that if alpha is bigger than 3/2, then it should be as if the order of the occupation time should be as if in the finite range asymmetric case. So namely, namely for, you know, the variance of the occupation time should be t to the 4/3. So so we there's some yeah, so there's that's also an open question.
More questions? Oh, sorry.
Yeah, no. Maybe I could ask a question, maybe a little bit of a technical one. In the previous slide, you have this condition. Where did you use this part 2 condition?
Yeah. In this here, I use the result from your paper with Cedric and Patricia because you consider this.
Oh, okay.
For this as this, so I assume the second condition.
Okay, thanks. Nice work.
Nice. More questions? No?
So I still have a question. So because so it seems to me that if you're able to show hydrodynamic limits, then you should be able also to prove the target particle problem. It's that's the impression I have. I mean, it's like the target particle problem for this particular type of long range systems. It's not really more difficult than the hydrodynamic limit problem. I don't know if because I think Sunder, I mean, in some cases you have hydrodynamic limits even for the asymmetric depending on parameters, no? Even for the asymmetric long range exclusion. So maybe something can be said in those cases, no?
Yeah, so we did the so if alpha is bigger than 2, then we rigorously proved that the hydrodynamic limit is the usual Burger's equation with the entropy solution, entropy condition. Mm-hmm. So if alpha is less than 2, then if I remember, it's been some time. We only showed tightness, and we were able to say that subsequential limits satisfy a fractional version of the Burger's equation. So it's asymmetric. So there's some PDE questions there about regularity of solutions and things like that, which we didn't touch at all.
Well, I don't remember if someone look at this question, but I think for alpha between 0 and 1, you can say something about hydrodynamic limits. Because for alpha, when alpha is smaller than 1, let's say that the Levy term dominates over the burgers. I don't know. Right, yeah.
Yeah, no. You know, the when alpha is small, then the proofs also would work for the symmetric evolutions. And I think Milton, you did the symmetric one.
Yeah.
And, so you have uniqueness of that weak limit, weak formulation. With asymmetry, if alpha is small, maybe there's some chance to maybe prove uniqueness. I'm not sure. But I think anyway, so I think that at the moment, what we were able to do is only just tightness.
Sorry, Sundar, but your proof works for any alpha less than 2, right? The only problem that you have is really the uniqueness of the weak solution.
Yeah, that's we left it at that. Yes.
All right.
Yeah, alpha. Yeah, all alpha.
Mm-hmm.
Alpha bigger than 2 or equal to 2. It's the short range equation.
Mm-hmm.
Alpha less than 2, it's some fractional equation for which we don't have uniqueness.
Mm-hmm. Good, right?
So do you have any ideas, Linjie, for the short range, non-nearest neighbor, asymmetric attack particle problem? This is showing central limit theorem. So you mentioned in the beginning that's open, right? So
yeah. So far I have no idea. Maybe this is this is open.
Yeah, so that's a very simply stated question that people might be interested to look at.
Right. Good. More questions? No? So let's thank Linjie. Thank you so much, Linjie.
Okay, thanks.
Thank you. Very nice. So we continue next week. And well, at the same time as usual. I think here we will change the time at some point, but not next week. So see you guys. See you next week. Bye-bye. Thank you, Linjie. And have a good night. For you, it's quite late.
Okay. Thanks.
Bye-bye.
See you.
See you.
Bye-bye.
Bye-bye. Sundar, I will send you the slides today. All right? Milton, eu vou falar com o Sundar e ele... Olha, tudo ok, não está?
Tudo ok.
Ok, boa. Eu ouço-te mal, estás longe. Esse micro tens que falar assim mesmo em frente, senão...
Assim? Tá.
É, assim sim, mas se falares assim já não se ouve bem.
Ah, tá bom.
Ok, muito bem. Pronto. Olha, vemo-nos, não sei, algum dia destes.
Muito bem.
Está tudo bem por aí, não está? Sim? Ok, vai lá. Beijo. Tchau.
Tchau.
Tchau, tchau.